Okay, so what we are going to be doing here is we're just going to be practicing our topic of conservation of momentum. So like we discussed in class, we know that momentum before an accident has to be equal to the momentum after an accident. And it doesn't really matter what kind of accident it is, collision, whatever. So we're just going to be taking a look at probably 2 or 3 problems involving conservation of momentum. So here is problem number 1. In this problem, we have a large car that has a mass of 1,500 kilograms. We have a smaller car that has a mass of 1,000 kilograms. We know that this car is going this way, going to the right at 10 meters per second. And then all we know is that this car, maybe it's going down the wrong way, but it's going that direction. So we have this information. Now, obviously, the collision happens. There we go. Love the sound effect. All right, and what we know about afterward is that the two cars, they stick together and have a total velocity of 0 meters per second. Okay, so there's the 1,500, there's the 1,000, and the question is going to be, what does this velocity have to be to make sure this is going to happen? Well, what kind of momentum do we have over here? We know that the collision basically acts like our equal sign, but the momentum that we have over here is exactly 0 uh, momentum, because this is, even though it's got a large mass to it, it's not moving at all. Okay, so we know that this guy has momentum. We can say that this is a mass times velocity over here. We know this has got some mass times velocity over here. They're not different. We can call this one mass A and velocity A, and mass B and velocity B if you want to talk about it. But we know that if you add them together, so MAVA plus MBVB, when you add them together, they have to be equal to 0. So we know that this velocity here has to be a negative number because of the fact that it's going the opposite way, but we're actually going to let the math do that for us. So if we're looking for VB, then we're going to go ahead and take this term to the other side. So mass B times VB is equal to minus mass A times VA. So getting VB by itself, VB is equal to a negative MAVA over MB. All right, so plugging in numbers, slipping in numbers, mass of A is 1,500 kilograms. We know it's traveling at 10 meters per second, and we're dividing it by 1,000 kilograms. So VB, and you could probably do this in your head if you really want to, and I'm going to check myself with a calculator. 1,500 times 10 divided by 1,000. Yeah, that's what I suspected. There we go. And that is 15 meters per second. And it is negative 15 meters per second. So we know that it's going 15 meters per second and going in the opposite direction. Okay, so this was a situation where we had both cars moving, but they cancel each other out. Let's start off with, or let's continue with another. Just remember that you can always pause and rewind to go back in the show. So this is question 2. We have an object that is sitting here, and there's an explosive in there, is what we know. So it explodes, and we have an object, part of it, that has a mass m, go that way, and this way, I guess I need to draw the arrow, goes this way, and we know that this has a mass 2m that goes off that direction. Okay, and we know that the velocity here is 10 meters per second. So the question is, what is the velocity that this guy is? Now, in this case, we actually don't know what m is, but and probably you're not going to need to know. We just need to kind of know the ratios, kind of like what we had up here. So let's start off with momentum. We know this guy is not going anywhere. It's just sitting there, waiting for that bomb to go off. So its momentum is exactly 0. Therefore, we have to make sure that the momentums cancel that over here. So it's almost like the exact opposite of what we had up here. So this is going to be regular mass multiplied by the velocity that we don't know, plus 2m times its velocity, which we do know to be 10 meters per second. Okay, so there's the total momentum. Now we're looking for this over here, so we're going to rearrange some things. We have 2m times 10 meters per second equals, and this is actually a negative, is equal to m times the velocity that we don't know. Okay, so if we want velocity, we can divide by an m. These m's will cancel out, so we didn't actually need to know what the mass is, and we get that the velocity is equal to a negative 20 meters per second. Okay. Now, if you look at conservation of momentum, you see that this is twice the mass than what this is. So to make sure that momentum equals, this has got to be twice the velocity of what this is, which is exactly what it comes out to be, negative 20 meters per second. So in this concept, you can actually discuss ratios. You can actually do some ratios with this if you are comfortable doing that, but sometimes ratios can get kind of messy. All right, so continue on. And we're going to do number 3. Now, number 3 is going to be different. Number 3 is going to be it's not going to be a perfectly elastic, not a perfectly inelastic. We're going to see what's going on here. So we got 2 cars. This one has 1,000 kilograms to it. Then it's going to hit a car that has 800 kilograms to it. We know this one is moving forward at 5 meters per second. Okay, and this one is moving the same direction with 2 meters per second. Okay, the collision. We have that this is the 1,000 kilogram car, and we're going to say that it's probably still moving this way. Notice that I said probably, we don't really know. But we have the other car that is the 800 is moving this way, and we have the velocity to be 5 meters per second. Okay, so 5 meters per second. So if we do momentum before and after, we notice that this has got momentum and this has got momentum. So we have the mass times velocity here, mass times velocity here. This has got momentum and this has got momentum. Now these all are not the same masses, they're not the same velocities. So you can do m1 v1, m2 v2, and m1 v1, m2 v2, realizing the fact that you're on 2 different equal signs, or 2 different sides of the equal sign. And these over here are final values that you add together, and these over here are initial values. So you can if you want to put i's on everything and put finals on things. The masses don't change, so they're still m1s and m2s. So what are we looking for? We're looking for this v1 final. v1 final. So we're going to put this term to the other side. So we have m1 v1 initial plus m2 v2 initial minus m2 v2 final equals m1 v1 final. It shouldn't be a dot. It's m1 final. So plugging in stuff, we can make things look a little bit prettier if we want to by factoring out this m2, but it doesn't necessarily matter. So we have 1,000 times, I'm dropping some units here just to make life a little bit easier, 1,000 times 5, that's m1 times v1i, plus m2, which is 800, multiplied by v2i, which is 2, minus 800, multiplied by v2f, which is 5, and this is equal to m1, which is 1,000, multiplied by vf. So once you get through all this, you divide by 1,000 to cancel that out, and you would have a final velocity. And I don't have this calculated, so I'm going to do my calculator. So 1,000 times 5 plus 800 times 2 minus 800 times 5. Okay, so whenever I plugged everything into the calculator, we got that it's 2.6, and this would be meters per second. So notice how this velocity came out to be a positive number. It came out to be a positive number, which means that we were correct in our judgment of how the direction of this velocity. What if we had said that this guy was something like 15, or so if I made that change, I'm going to make it in green. What if we said it was 15? So how would that change? Well, this would become a 15, and it's possible that this whole number over here would turn into a negative number. And if it turned into a negative number, then we would actually know that if this shot off at 15 meters per second, this one would actually have to recoil to make sure that conservation of momentum happened. So I'm going to leave you to make sure that you calculate that and see how this number changes. So these are just practice problems. Go back and review these if you need to. And this is just over conservation of momentum.